Hello everyone. Today we will be talking about series. I'm sure most of you know what is meant by a series. Basically, it is an infinite sum. We all know what a finite sum is, but point of today's lecture is that we cannot generalize it to an infinite sum. For example, consider an equal to minus 1 raised to n minus 1. So if I now consider an infinite sum, summation n, what do I get? I will get minus 1 raised to 0 plus minus 1 raised to 1 and so on. So I will have 1 plus minus 1 plus 1 plus minus 1 and so on. So depending on how I group, I might get summation n equal to, if I group like this, I will get 1 minus 1 plus 1 minus 1 and so on, which would tempt me to write 0. On the other hand, if I write this as 1 plus and then group these terms, so minus 1 plus 1 plus minus 1 plus 1 and so on, I will be tempted to write this as 1. So essentially, if I try to treat an infinite sum like a finite sum, I am concluding 0 is equal to 1, which is ridiculous. Hence, we cannot simply take a series as a generalization of finite sum to an infinite sum. We need a special way of defining that series. Okay, so we need to first define what is meant by an infinite series, and then we need to talk about sum of that series in terms of convergence of sequences, which we have already studied. So what is an infinite series? Let me write a formal definition. Given a sequence an, an infinite series is defined as an infinite sum. An infinite series is defined as a formal sum summation an. But we saw just now that this cannot simply be defined as taking an actual sum. Okay, hence we introduced one more term called as partial sums. Okay, or to be more precise, we need to talk about a sequence of partial sums. What do I mean by partial sums? As the name suggests, it has to be sum of some parts. So let me define S1 as A1, S2 as A1 plus A2, Sn as A1 plus A2 plus An. Okay, so Sn is the sum of first n terms. So these are known as partial sums, and hence Sn associated with this series an, this is known as a sequence of partial sums. You can see if my ai's are positive, or basically if ai's are non-negative, then this sequence will be, the sequence Sn will be a non-decreasing sequence. Okay, and now from this term I can actually write limit n going to infinity Sn is same as what we mean by an infinite sum summation an. Okay, or I would write summation ak because I already have n on left hand side. Hence, limit of the convergent series or sum of the series will basically be limit of the sequence of partial sums. Therefore, how do we define a convergent or a divergent series? Convergent or divergent series. A series summation an is said to converge or diverge. Okay, I will keep this in bracket. If the corresponding sequence of partial sums converges or diverges. If the corresponding sequence of partial sums converges, or in the case of divergence, the corresponding sequence should diverge. Okay, so this is a very important definition. We will see a few more examples later of convergence and divergence, but before that we will define two more terms, something which is known as absolute convergence and conditional convergence. So what is an absolute convergence? So a series summation an is said to converge absolutely if summation mod an converges. Okay, if a series of absolute of terms converges, then we say that the original series converges absolutely. Now you can see from this definition that if a series consists of only non-negative terms, then convergence is actually same as absolute convergence. But in general, this need not be true. Hence, we have what is known as conditional convergence. So, if summation an converges, but summation mod an does not converge, then we say that the series converges only conditionally. Then we say that the series converges conditionally. Okay. So these are some basic definitions related to convergence of series. Now we will see a few examples. First, we will try with very simple examples. Suppose I consider a constant series. Okay, so if I simply consider an equal to a constant c, then summation an is summation c. So if I consider partial sum, s1 will be c, s2 will be c plus c, in general Sn will be Nc. And from Archimedean property, we know that the set of natural numbers is not bounded, and hence this diverges to plus infinity. Therefore, a constant series also diverges to infinity. Okay. In fact, this tells me why I cannot have a discrete uniform distribution on a countable support. Because discrete uniform means it will have constant probabilities. So if I have constant probabilities on a countable support, their addition will not be finite. Okay, so I cannot make sum of the all probabilities as 1. Okay, so this is one trivial example. Let me consider another example which is probably known to most of you, a geometric series. You may not have used the word geometric series, but you have seen geometric progression definitely. So suppose we define an as z raised to n for every n greater than or equal to 0. We define from 0. Okay, and we assume that mod z is less than 1, strictly less than 1. Then summation an is summation z raised to n s1. So I will start with s0 as z raised to 0, so 1. s1 as z raised to 0 plus z raised to 1, which is 1 plus z, and so on. So Sn will be 1 plus z plus z raised to n, which we know from the geometric progression is 1 minus z raised to n upon 1 minus z. So if I take limit on both the sides, as n goes to infinity, I will be left with 1 minus, this goes to 0 upon 1 minus z, which is 1 upon 1 minus z. Okay, so if I have a geometric series, then summation z raised to n is simply 1 upon 1 minus z, provided mod z is less than 1. Okay, what happens if mod z is greater than 1 or equal to 1? If mod z is equal to 1, then this becomes a constant series and hence it diverges. If mod z becomes greater than 1, then still the sum is similar. It is z raised to n minus 1 upon z minus 1. But then we know that this z raised to n does not converge. It diverges to infinity and denominator is constant. So the series also diverges. Okay. Let me now introduce one more very powerful technique of finding limit of a series. So this is known as telescoping series. Okay. Telescoping series. Let me first define what is this, and then we will see a couple of applications of this technique. Let an and bn be two sequences such that an is equal to bn plus 1 minus bn. So they are not arbitrary sequences, they are related to each other in this manner. That is, sum of the two consecutive terms of bn is same as an. Now what happens in this case? My s1 is simply a1 is b2 minus b1. S2 is a1 plus a2. a1 is b2 minus b1 plus a2 is b3 minus b2. Okay, so this is same as b3 minus b1. S3 is a1 plus a2 plus a3. So this is b2 minus b1 plus b3 minus b2 plus b4 minus b3. So my b2 gets cancelled, B3 gets cancelled, so I am left with B4 minus B1. Proceed in this manner, or via induction we can prove that Sn is actually Bn plus 1 minus Bn. Okay, Sn is Bn plus 1 minus Bn, and as a result, Sn is Bn plus 1 minus B1. Okay, I accidentally wrote N. B1. Okay, because S2 is B3 minus B1, S3 is B4 minus B1, so B1 is there everywhere. So Sn is Bn plus 1 minus B1. As a result, limit Sn will be limit Bn plus 1 minus B1. Okay, so the sequence of partial sums converges if Bn converges. Okay, this is a very important result, and we can use it to find limit of some apparently complicated series. Okay, let us try one simple example first and then one slightly bigger example. Okay, so let me define an as 1 upon n into n plus 1, and of course we are interested in finding out what happens to summation an. Okay, now what happens to summation an? If I directly see here, if I directly write summation an, then it is 1. When I put n equal to 1, I get 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 and so on, and it seems a bit difficult to get this limit. Okay, but if I note that 1 upon n into n plus 1 can actually be written as 1 upon n minus 1 upon n plus 1, because see, numerator will be n plus 1 minus n, that is 1, divided by n into n plus 1. Okay, so this is my an, and my telescoping series notation says that I should have an as bn plus 1 minus bn. Okay, so I can define bn plus 1 as this quantity. Okay, so this I can define as bn plus 1, then this becomes minus bn, and this is what I want, bn plus 1 minus bn. Okay, therefore let bn equal to minus 1 by n, which implies an is equal to bn plus 1 minus bn. Hence we have telescoping series, therefore summation an is same as limit of Sn, which is same as limit of bn plus 1 minus b1. Okay, because we have shown this earlier. So what is bn plus 1 here, limit of bn plus 1? So that would be limit of minus 1 upon n plus 1 minus b1 is 1 upon 2, correct? Sorry, not 2, b1 is simply 1. So this goes to 0 and this becomes 1. Therefore, sum over 1 upon n into n plus 1 is simply 1. Okay. So I have some optional homework for you. In R, use R to compute S1, S2, etc. for this series, and then plot and see if it converges to 1. So if 1 is here, it should converge to 1. So this is how the graph should look like. Okay, increasing graph, and it should go to 1. Okay, so check if that happens. Let me now take one more example of series whose limit we can evaluate via this technique of telescoping. Okay, so now this is slightly difficult to look at, because in the earlier example it was easy to visualize it as a telescoping series. Here that is not the case, but that is one of the reason why we are taking it. Okay, so because we want to emphasize that the importance of telescoping technique. So let me define an as n upon n raised to 4 plus n square plus 1. Okay, so I have this as an, and I want to check whether the series summation n converges, and if it converges, can I find the limit? Okay, now of course this is not the form that we like, so what can be changed? So in the denominator, if I make denominator whole square, my life could become easy. So what can I do? I could write an as, so to make denominator whole square, I would need 2n square plus 1. So I will need to subtract 1n square. Okay, so this is whole square. So this is like, if I call this as a square and as b square, then this becomes n upon a minus b into a plus b. So let me write that. So this is n square plus 1 whole square. Okay, so n square plus 1 minus, so this is a minus b means n, into n square plus 1 plus n. Okay, now see, just like here, the difference in n and n plus 1 was 1, and hence we could write this as a telescoping series. In the current scenario, difference between this and this is 2n. So if I bring in half, then I could possibly write this as a telescoping series. So let me try this as half 1 upon, whichever is bigger one I will take that first. So I will have n square minus n plus 1 minus 1 upon n square plus n plus 1. Let us check if this is correct. So numerator here will be n square plus n plus 1 minus, here I will have n square minus n plus 1. So n square will get cancelled, 1 will get cancelled, I will be left with 2n, which is nothing but I want, because 2 will get cancelled. Okay, so we have to define bn as minus half n square minus n plus 1. Coincidentally, here also I have to define bn as negative, because if I cannot define bn as this positive term, if I define bn as this positive term, then bn plus 1 cannot be this. Okay, whereas with this bn, now bn plus 1 will be minus 1 upon 2 into bracket n plus 1 whole square minus n plus 1 plus 1, which is equal to minus 1 upon 2 into n plus 1 whole square will be n square plus 2n plus 1 minus n minus 1 plus 1. Okay, so 1 goes, then this 2n minus n becomes n, so I am left with minus 1 upon 2 into bracket n square plus n plus 1, which is what we want. Okay, is it okay? So my an now becomes bn plus 1 minus bn, and hence again summation an will be same as by telescoping series limit of bn plus 1 minus b1. Limit of bn plus 1 will be limit of minus 1 upon half bn plus 1 will be n square plus n plus 1 minus b1 will be 1 upon 1. So b1 will be 1 upon 2 into 1 minus 1 plus 1. 1 minus 1 plus 1. Okay. So this is here, because n is going to infinity, first term will go to 0. So I am left with minus, and of course this minus sign is there. So minus minus plus, so I am left with half. Okay. So this series, even though it looks complicated, it converges to half. So this tells us the importance of telescoping series in evaluating limits or sums of series where the sums look difficult. Okay. Now we have considered two simple series, constant. For example, one was constant series and other one was geometric series. Then we have considered two slightly complicated series. Now let me try some moderate series. Okay. For example, one commonly known series is summation 1 by n. Okay, so a n equal to 1 by n, and we are of course interested in finding out whether summation 1 by n converges or diverges. Okay, this is also known as harmonic series. What is summation 1 by n? So a1 equal to 1, so s1 is 1, s2 is equal to a1 plus a2, that is 1 plus half, s3 is equal to a1 plus a2 plus a3 plus a4, which is 1 plus half plus 1 by 3 plus 1 by 4. Okay, s4 is equal to 1 plus half plus 1 by 3 plus 1 by 4. Now notice that in this bracket 1 by 3 is larger, so I can say this is larger than 1 plus half plus 1 by 4 plus 1 by 4. So this would make it 1 plus half plus 2 into 1 by 4, which will make it 1 plus 2 times half. Okay, so S4 is greater than 1 plus 2 times half. S4 I could actually write as S of 2 square. So this 2 is coming here. Let me try S8. So S8 will be S2 raised to 3. So it will be A1 plus A2 plus A8. So there I would write it as 1 plus half plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. So this is greater than 1 plus half plus 2 times 1 by 4 plus this, we know every term is greater than 1 by 8. So this is 4 times 1 by 8. So this is equal to 1 plus half plus 2 times 1 by 4 plus 4 times 1 by 8 is actually half, and this is also half. So this is 1 plus 3 times half. Okay. So what we are saying in general is S2 raised to k is greater than 1 plus k times half, and we know k belongs to n, so this diverges to infinity, and as a result S2 raised to k is always larger than whatever number you want to make it large. Therefore Sn is an unbounded sequence. Okay, Sn is an unbounded sequence, and therefore Sn cannot converge, because we know that every sequence is convergent. So Sn does not converge. Sn does not converge means the series summation 1 by n does not converge. Okay. So today let me stop here. In the next lecture we will try some theoretical results about this convergence of series. Thank you.